continue our lecture series on numerical methods in civil engineering, we are going to continue our discussion on iterative methods for solving linear systems. Last time we looked at iterative methods in general, and specifically we looked at what is probably the simplest iterative method for solving linear systems, Jacobi's method, and we obtained convergence criteria for the Jacobi's method. We figured out under what conditions the repeated iterations using a constant coefficient matrix leads to convergence solutions. We also talked about Gauss-Seidel's method, which is a variation of the Jacobi method, where instead of continuing with the old iterates for an entirely new cycle, we update the new values of the iterates as they occur during the solution. So, we talked about Gauss-Seidel. This time we are going to talk about convergence of Gauss-Seidel's method. Recall, to examine the convergence of iterative methods, it is convenient to write the update algorithm in the generalized form of a stationary iterative method, where x k plus 1, which is the solution at the k plus 1th iteration, is equal to b, some coefficient matrix which depends on the iteration algorithm, times x k, where x k is the solution from the previous iteration plus a constant vector c, and we continue this iteration for k equal to 0, 1, 2 and so on until we reach convergence, when x k plus 1 is equal to x k within a certain tolerance, and both of them can be taken to be both of them are close to the true solution within certain error norms. Recall the Gauss-Seidel's method in this form, in the form x k plus 1 is equal to b x k plus c, can be written if we represent the matrix B by L plus U, where L plus U are lower and upper triangular matrices which are formed from my original coefficient matrix A. Each of them, recall, has 0 on its diagonals, and D is the actual is a diagonal matrix which we defined last time. So, x k plus 1 is equal to minus L plus U x k plus D inverse B. That is, if we write the Gauss-Seidel method in the generalized form of a stationary iterative method. Hence, B for Gauss-Seidel's method is minus I plus L inverse U. This also we have seen last time. Also, we recall that we found that a necessary and sufficient condition for convergence of a stationary iterative method is that the spectral radius of B be less than 1. That is, the largest eigenvalue of B must have norm magnitude less than 1. In that case, that is both a necessary as well as a sufficient condition for the convergence of a stationary iterative method. However, it is not easy to know a priori the spectral radius of B. So, it's not always possible to, before doing the iterations, to solve the eigenvalue problem and find out the largest eigenvalue of B. That is simply too cumbersome and too troublesome and too expensive. Hence, we would like to know, come up with some alternative criteria that we can use to determine if our stationary iterative method is going to converge, a criteria which does not involve doing a spectral analysis and figuring out the eigenvalues of B. For Jacobi's method, we found that if the matrix B is diagonally dominant, that is a sufficient condition for convergence. That is a sufficient condition, but it is not a necessary condition. It is a sufficient condition for convergence. So, we would like to find something similar for Gauss-Seidel's method, obtain a convergence criteria which is relatively easy to use and which does not require finding the largest eigenvalue of B. We recall that for any consistent matrix vector norm, for instance the infinite norm, we have in the infinite norm of a matrix is equal to that matrix operating on a vector that gives me a vector. For instance, if I want to find the infinite norm of BGS, where GS represents the Gauss Seidel, right, B for Gauss Seidel, that we can find that out. We can find the infinite norm by taking the product of BGS, the coefficient B matrix for Gauss Seidel, with any arbitrary vector x, such that the norm of x is not equal to 0, that is x is not the 0 vector. So, BGS times product with x, we find the norm of that divided by the x divided by the norm of x, and whatever value, if we maximize that, that is going to be my infinite norm for the matrix. This is our definition of a consistent norm, which we talked about earlier on. Let us denote BGS x is equal to y. In that case, the infinite norm of BGS is equal to maximum of y infinite norm divided by infinite norm of x. When you maximize it, that gives me the infinite norm of BGS. Let us suppose that the infinite norm of y, which is by definition the maximum of the absolute of all the components, absolute value of the components, we calculate the absolute value of the components and take the maximum of that over all the components, that by definition is the infinite norm of y. And let us suppose in that y vector the kth entry, the kth component gives me the norm of y infinity. So, this is basically the largest entry in the y vector. Let us also recall that the Gauss-Seidel's update formula y is equal to minus Ly minus Ux plus B d inverse C, and let us neglect the constant term d inverse C for the time being. We consider the equation y is equal to minus Ly minus Ux. Why do we ignore the constant term d inverse C? Well, we are interested in the convergence, and once we are interested in the convergence, we are interested in the convergence of y, right? We are interested in the convergence of y. So, the constant term does not play a big role in the convergence. Let us consider in particular the kth equation in this system. This system, I mean this system. Let us consider this simplified system where we have got rid of the constant vector d inverse C, because we said that is not important for convergence, for studying the convergence of this method, and we say that we consider this y is equal to minus Ly minus Ux. And we know that we know that since the infinite norm of y is given by the norm of by the kth term in y. So, basically we find out the kth term, right, on the both the left hand side and the right hand side, and the kth term is equal to sigma j equal to 1 to k minus 1 L k j y j minus u k j x j. So, this is the lower triangular part, this is the upper triangular part, and you can see this is k, L k and u k, because we are only considering the kth equation in this system of equations. Y k is equal to the kth row of this matrix times the y vector, the kth row of the u matrix times the x vector. So, we can write that like that, just taking the norm on both sides, right, and this is going to be less than this plus this. Again, this minus this is going to be less than this absolute norm of this plus norm of this. Recall we have done this before, and this again Lkj we can write as Akj by Akk by definition, because the lower triangular matrix is just the original matrix scaled by the scaled by D inverse, right? D inverse times the original matrix, the lower triangular part of the original matrix scaled by D inverse, that is my L. So, that is this term, and this is my upper triangular matrix, which is basically the U, which is basically the upper triangular part of A scaled by D inverse. That is why you have this AKK. So, this is less than that, and this is equal to this, while that is equal to that. Since we know that mod of yk is greater than yj for all j not equal to k, because we have assumed that yk is the term in y, the entry in y which has the largest absolute value. So, we can write mod of y infinity is lesser than or equal to this term, and now I am going to replace yj by mod of yk, right. So, since this is yj, but since this is always greater than every j except k, if I replace this by mod of yk, the right hand side is going to be greater than this, right. Similarly, instead of xj, if I replace it by the maximum component of x, instead of summing it over all the components, I sum it all the time with the maximum component of x. Obviously, that is an upper bound on this, right. So, if I replace that by that, so but this is nothing but y infinity, that is nothing but x infinity. So, we can write this as, if we write this as xk and write this as rk, we can write this mod of y infinity is lesser than or equal to sk times mod of y infinity plus rk times mod of x infinity. So, we get, again bringing by mod of y infinity to the left hand side, the infinite norm of y, we bring it to the left hand side. We can write this as mod of y infinity by mod of x infinity is lesser than or equal to rk divided by 1 minus sk, right. So, 1 minus sk mod of y, infinite norm of y, is lesser than or equal to rk times infinite norm of x. So, infinite norm of y divided by infinite norm of x is lesser than or equal to rk divided by 1 minus xk and sk. And recall that we said that BGS, infinite norm of BGS, is equal to maximum of y infinity by x infinity. So, we can write BGS is lesser than or equal to maximum of Ri by 1 minus Si, right, because this is equal to that, and we saw that was maximum of this, maximum over this. So, maximum of Ri by 1 minus Si, I is equal to 1 to n. Since maximum of Ri, obviously because this maximum of Ri 1 minus Si must be greater than any value rk 1 minus sk. So, if we replace this on the right and replace this with maximum of that, this has got to be less than this. But from the definition of Ri and Si, it can be shown that for diagonally dominant matrices, Ri plus Si is less than 1. Why is that? Well, Ri plus Si, we denoted Ri to be this, and we denoted Rk to be this and Sk to be this. So, if we write Ri plus Si, that is, so just replacing k with I. So, that is this plus this, which is equal to, you can see the sum is over j is equal to 1 to k minus 1, and here the sum is over k plus 1 to n. So, the sum is actually over j is equal to 1 to n, other than j not, when j is not equal to I, right. So, this is equal to mod of Aij by mod of Aii, which is always less than 1 if the matrix is diagonally dominant, right. That is the definition of diagonal dominance. The sum of the absolute values of the off diagonal terms is going to be less than the absolute value of the diagonal term. So, that is when the matrix is strictly diagonally dominant. So, if the matrix is strictly diagonally dominant, Ri plus Si will be less than 1, which means that BGS must be less than 1. Hence, again similar to Jacobi's method, we see that Gauss-Seidel's method is convergent when the B matrix is diagonally dominant. Thus, both Gauss-Seidel's and Jacobi's method are bound to converge to the true solution with increase in the number of iterations if the B matrix is diagonally dominant. If my B matrix, which in case of Gauss-Seidel is given by this which for Gauss-Seidel is given by this, if this matrix is diagonally dominant, then I am guaranteed that my Gauss-Seidel iteration is going to converge after a certain number of iterations. So, that is convergence. However, what is important is also the rate of convergence. Something might converge, but it may turn out that it converges so slowly that it might be practically useless. So, if something converges after 1,000,000 iterations, that is not going to be useful for any practical computational purposes. So, we are also interested not only in the fact that the iterative method converges, it must converge in a reasonable number of iterations. Therefore, the rate of convergence is also very important, and we recall that the rate of convergence depends on this factor R, which is equal to minus log of rho b, which we call the asymptotic rate of convergence, rho b being the spectral radius of B. The rate of convergence depends on how fast the error at iteration k, which I denote as mod of x k minus x, goes to 0 as k the number of iterations increases. So, suppose at iteration k I have a certain error which is given by this. I would like to know the rate of if it converges fast, then it would converge to the error would go down fast as the number of iterations increases. To get an estimate of the error in x k, we use the following relation: x k minus x is equal to, recall that x k is equal to b x k minus 1 plus c. That is standard for a stationary iterative method, right? So, we can write x k minus x as b minus b x k minus x k minus 1 plus b x k minus x. So, basically minus b x k plus b x k cancels out, we have b x k minus 1 and minus b x, and recall that x is equal to b x plus c. So, we are recovering this equation. So, basically we are writing this equation in a slightly different form. This equation I am rewriting it in a slightly different form. Why is x is equal to b x plus c? Because at convergence, after it has converged, x k plus 1 is almost equal to x k minus 1, right. So, x k is equal to b x plus c, where x is the true solution, x is the converged solution. Once it has converged, x is equal to b x plus c. So, we use this equation to get an estimate for the error. Let us see what we do. If mod of b is equal to beta less than 1, so if the infinite norm of b is suppose beta and suppose it is less than 1, which we know is necessary for convergence, we get mod of x k minus x, taking the norm on both sides. Norm of x k minus x is lesser than or equal to norm of b, norm of x k minus 1 plus norm of b x k minus x. So, just taking the norm of both sides and using the fact that norm of this operating on that is lesser than or equal to norm of this times the norm of that. and using the fact that norm of B is equal to beta, we get beta times norm of xk minus xk minus 1 plus beta times norm of xk minus x. Again, bringing this term to the left hand side, we have 1 minus beta norm of xk minus x is equal to beta times norm of xk minus xk minus 1. Therefore, norm of xk minus 1 x is less than or equal to beta by 1 minus beta norm of xk minus xk minus 1. We will see that only when beta is lesser than or equal to 5, this term is going to be less than 1, right. This term is going to be less than 1, beta by 1 minus beta is going to be less than 1 only if beta is lesser than or equal to half. Then we can be assured that means this term is less than 1. So, that means that the iterate xk is sufficiently close to the true solution, that is its difference from the true solution norm of xk minus x, the difference of xk with the true solution is less than or equal to the magnitude of the last correction. This is the last correction xk minus 1. If this factor is less than 1, that means this difference is less than the magnitude of the last correction. So, in that case, once we satisfy that criteria, we can stop our iteration. We say that our solution xk has almost converged because the change in xk is closer to the true solution than the change from the last iteration value. So, that is when it has converged. The expression star, however, does not take into account round off error, right. So, we are assuming that everything is being done in infinite precision when we write that equation, right. So, it does not take into account rounding error. Thus, even when the structure of the stationary iterative method indicates that the error at iteration k satisfies this bound, even when we think that it has satisfied this bound, round off errors in the arithmetic operations of the algorithm may lead to violation of the bound. Next, we talk about a slight modification to the Gauss-Seidel method, which substantially improves the convergence of Gauss-Seidel's algorithm. Let us recall that the Gauss-Seidel algorithm is given by xi k plus 1 is equal to this, where this is the lower triangular part comprising the values of the elements which have already been found from the new iteration, the values of the elements which have already been found from the new iteration. This involves the values which are using from the old iteration, and this is the right hand side. So, we recall this is our Gauss-Seidel algorithm. Then we denote xi k plus 1 is equal to xi k plus ri k for the ith equation. In that case, we can write xi k plus 1 is equal to, this part remains the same, but this part, instead of summing from j equal to I plus 1 to n, now I am going to sum from j is equal to I to n. So, I am adding an extra term here. What is that extra term? The term for j is equal to I, which is nothing but aii xi k, right. Aii xi k divided by aii, that means I am adding a minus xi k, and I am compensating for that by adding another xi k. So, I rewrite this like this, and since we have denoted xi k plus 1 is equal to xi k plus ri k, so this term, this whole thing becomes my ri k, right. This whole thing becomes my ri k. If the iteration method is written as xi, so recall what is Gauss-Seidel? Gauss-Seidel says that xi k plus 1 is equal to xi k plus ri k. So, now we are saying that we are not going to use full Gauss-Seidel. We are going to use xi k plus 1 is equal to xi k plus omega Rik, right. Omega is a scalar, right, some scalar times Rik. So, we are just changing the Gauss-Seidel algorithm. Instead of using the full Rik, which we recover when omega is equal to 1, we are going to use some fraction, either we will see what are the allowable values of omega, but for the time being let us suppose that we are multiplying this by a scalar times Rik instead of just taking Rik. Then we have what is known as the successive over relaxation method, or the SOR method, and the factor omega is known as the relaxation parameter, and it is chosen to maximize the rate of convergence of the algorithm. So, pure Gauss-Seidel xik plus 1 is equal to xik plus Rik. SOR method, instead of taking Rik, we are multiplying Rik, we are scaling the Riks with a scalar omega, and we are going to choose this scalar omega so that we get maximum rate of convergence of the algorithm. Recall again that for Gauss-Seidel our iteration matrix B is given by BGS is equal to minus I plus L inverse U, which we have seen several times. For the SOR method, we get a modified B matrix B omega, which we denote by B omega, which is equal to minus I plus omega L inverse 1 minus omega I minus omega U. I have not actually shown this, but I am asking you to take this for granted. It can be shown quite easily that if instead of taking xik plus 1 is equal to xik plus Rik, I replace xik plus 1 is equal to xik plus the omega Rik, then my B matrix changes from this matrix to this matrix. So, if we use the SOR method, my B matrix changes from this to this. From this, if we take determinant of both sides, what do we have? Determinant of B omega is equal to determinant of this times determinant of that, and recall that determinant of A inverse is equal to 1 by determinant of A. So, we are going to use that. Determinant of B inverse therefore is equal to 1 by determinant of this part, right, and times the determinant of 1 minus omega I minus omega U, which is this part. But recall that the determinant of a triangular matrix, which we have seen several times before, is given by the product of the diagonal terms, right, product of the terms on the principal diagonal, and by definition we have defined L and U to have zeros on their principal diagonal. So, obviously, the determinant of both L and U are 0. Hence, the diagonal elements of I plus omega L, this matrix, this term is not going to contribute anything, right. So, on the diagonal are each equal to 1, right. So, this is going to be a triangular matrix, right, because this is a lower triangular matrix. To this we are adding the identity matrix. So, the result is going to remain a triangular matrix, a lower triangular matrix, and for a lower triangular matrix the determinant is the product of the diagonal terms, and since the diagonal terms of L are 0, the diagonal terms of I plus omega L are nothing but 1. So, this determinant is going to be 1, right, and the diagonal elements of 1 minus omega I minus omega U, similarly again U has got zeros on its diagonal. So, on its diagonal of this entire matrix we have 1 minus omega, each diagonal term is equal to 1 minus omega. So, this determinant is going to be 1 minus omega to the power n, right, where n is the size of the matrix. So, this gives me determinant of B omega is equal to 1 minus omega n. But let us go back, take a step back and recall that determinant of a matrix is equal to the product of its eigenvalues. We have seen that before. Therefore, what do we have? We have determinant of B omega, which is equal to 1 minus omega to the power n must be equal to lambda 1, lambda 2 through lambda n, where lambda 1, lambda 2 through lambda n are the eigenvalues of B omega. Therefore, the maximum eigenvalue must be greater than or equal to 1 minus omega. Why? Because this product of all these eigenvalues is equal to 1 minus omega to the power n. Therefore, the maximum value must be greater than or equal to 1 minus omega, right. If you think a minute about it, that should be clear. This is the product of all the eigenvalues is this. So, it is clear that its maximum value must be greater than the nth root of this, right. So, maximum lambda I must be greater than or equal to mod of 1 minus omega. And recall also that for convergence, what is our requirement? The necessary and sufficient condition for convergence is that the maximum eigenvalue of B has to be less than 1. So, maximum lambda I over I must be less than or equal to 1. We therefore have this condition, maximum lambda over I is greater than or equal to 1, but this is again greater than or equal to 1 minus omega, which mod of 1 minus omega, which implies mod of 1 minus omega must be lesser than or equal to 1, which means that omega must lie between 0 and 2. Thus, what do we see? That the SOR method, the successive over relaxation method, is only going to converge when omega lies between 0 and 2. So, this value of omega, we cannot choose any arbitrary value of omega and hope that we are going to converge. Only if we choose omega lying between 0 and 2 are we going to get convergence. And it can be shown that if the coefficient matrix A is symmetric and positive definite, then the SOR method always converges when omega lies between 0 and 2. So, it is a necessary as well as a sufficient condition, right. So, that was our discussion about the Gauss-Seidel method and a variation of the Gauss-Seidel method. And before moving on to something else, this is a good time to talk about certain linear systems which are also amenable to iterative solutions. For instance, systems specifically, but we want to talk about systems which are overdetermined, where we have number of equations. The number of equations is more than the number of unknowns, which is an overdetermined system. For instance, that means basically we are considering a system Ax is equal to B such that the number of rows of A, m, is greater than the number of columns, n. An overdetermined linear system may occur during experimental readings when there are more measurements than the number of unknowns. If we are trying to find some values x, right, and we are measuring a certain set, we are setting certain parameters which are governed by the entries in A, and we are looking at certain results, and from those results and those parameters we want to find out the values of our unknown variables x. We perform a large number of experiments, more experiments than there are unknowns. So, in that case we come up with an overdetermined system, and overdetermined systems do not have unique solutions. You can understand, right? You have more equations than unknowns, so there are no unique solutions, and in that case it becomes necessary to find the best solution. Best solution means something which best fits the data. Suppose we do a whole number of experiments, right, and we have a lot of parameters, we vary a lot of parameters and we find a lot of results, but our independent variables, the number of independent variables are less than the number of readings that we have taken. So, we want to find out what values of the independent variables, what are the values of independent variables which best fit our experimental data, right, which best fit our values B, which we have obtained as consequent to our experiment. So, it is necessary to find the solution that best fits the data. So, these are suppose our experimental readings, and A represents the parameters we have varied, right. And these we have varied the parameters, we have found our experimental results, and now we are interested in finding the independent values of the independent variables which best fit our experimental results B, right. So, basically we are interested in minimizing the residual. Residual we define as B minus Ax. So, again this becomes an iteration, it can be solved iteratively, right. We try with successive values of x, right, find out what is the residual and continue iterating till you get a relatively small or acceptably small value of the residual. But it turns out that instead of doing that, if we try to minimize the L2 norm of the residual, we can come up with a more systematic solution. So, basically we find the norm of the residual in the L2 sense, right. Basically we take the r dotted with r, we find the scalar and take the square root of that, which gives me the L2 norm. And then if we try to find the value of x which minimizes the value of the residual, we try to find the value of x which minimizes the value of the residual, we get what is known as the least squares solution. You can see why it is called least squares. It is the value of x which minimizes the square root of the inner product of r with r. The least squares solution is such that the resultant residual is orthogonal to the vector space spanned by the columns of the coefficient matrix. Basically A transpose R is equal to 0. Recall we defined R is equal to B minus Ax, right. B minus X, if we take the projection on A transpose B minus Ax means we are taking the projection of this vector B minus Ax on the space that is spanned by the columns of A, right. That linear space which is spanned by the columns of A, which has got basis vectors which are given by each individual column of A, right. If we take the projection of B minus X on that space which is spanned by the columns of A, then we get 0. So, basically the residual has 0 component in the space that is spanned by the columns of A. So, it is orthogonal to the space that is to the vector space that is spanned by the columns of the coefficient matrix A. If the above condition is satisfied, we can show that for any vector y which is not equal to x, x being the vector which minimizes the residual, for any vector y which is not equal to x, the residual which we now denote by ry, which is b minus ay instead of ax, right. Y is different from x, x minimizes the residual, that in that case b minus ay is always going to be greater than b minus ax. So, if we find x such that x satisfies this condition, that any vector y will give me a larger residual, right. This is sort of obvious, right, because we are finding x which minimizes the residual. So, any vector y is going to give me a larger residual. It is intuitively clear, but it can be proved quite easily also. So, just let us go through the proof once. Ry is equal to, let us recall how we defined Ry is equal to b minus ay, right. So, Ry is equal to b minus, instead of writing b minus ay, I write it as b minus ax plus ax minus ay, but this is equal to Rx, right, my residual for my least square solution x, right. B minus ax is equal to Rx plus ax minus y. I take dot product in a product on both sides. So, Ry dotted with Ry is equal to Rx dotted with Rx plus Rx dotted with this plus Ax minus y dotted with that plus Ax minus y dotted with Ax minus y, where Ax minus y I am treating it as a vector, right. a matrix operating on a vector after all gives me always a vector. So, this is a vector dotted with that. So, this is nothing but that. This is, we can write R x dotted with A x minus y as A transpose R x dotted with x minus y. Similarly, A x minus y I can write as x minus y dotted with A transpose R x. Can verify, but this is always true. This is how a transpose is defined, right? The mathematical definition of transpose is like this. So, this is this you can verify, and this again we can write, again we do the same trick, we bring x minus y A transpose A x minus y. So, these are identical equal, but let us look at this. A transpose R x is equal to 0 by definition. Why? Because that is what we have here, right? That is exactly what we have here. So, this term goes to 0, this term goes to 0 because A transpose R x goes to 0, and we are left with R x dotted with R x plus x minus y A transpose A x minus y, and this is now, then we rewrite this as the square of the norm of R x R y is equal to the square of the norm of R x, and then we again treat this as a vector x minus y A transpose A x minus y I can write as A x minus y dotted with A x minus y. So, it is as if I am taking the dot product, inner product of a vector A x minus y, and that I can write as A x minus y whole square. Since this is not going to be 0 for x not equal to y, then we can say that R y square is always going to be greater than R x square, because this term is not going to be 0. This is something intuitive, but this is just a proof for that. Recall that the least square solution yields a residual that is orthogonal to the space spanned by the columns of A. So, the residual B minus A x is orthogonal to the space, to the vector space spanned by the columns of A. So, I consider each column of A, they are linearly independent and they form a basis for the space. Suppose the dimension of A is n by n, so they form a basis for the vector space of dimension n, and the residual is nothing but B minus A x. It is, we have taken the projection onto the space spanned by the columns of A. We have taken the projection of B onto the space that is spanned by the columns of A, and whatever is left is the residual. Thus, the least square procedure splits B into two parts, A x and R, with A x by definition belonging to the space R A. Why does A x belong by definition to the space R A? Because after all, what is A x? A x is nothing but a linear combination of the columns of A, right? If you write it out, if you expand it, A x is nothing but the column 1 of A times x 1 plus column 2 of A times x 2, and so on and so forth. So, A x is nothing but a linear combination of the columns of A, and therefore, it must belong to the space R A, which is spanned by the columns of A, and then we have R, which is orthogonal to the space. From this expression, it is clear that the least square solution satisfies this criterion, A transpose A x is equal to A transpose B. Right, just expanding this out, right? A transpose B is equal to A transpose A x, right? This is equal to 0. So, A transpose B is equal to A transpose A x. So, that is what we have written out here, and therefore, we can get the least square solution by actually solving this system if it is at all solvable, right? If this system is solvable, so what will make this system solvable? If this matrix is invertible, right? If A transpose A is non-singular, we can find the least square solution by solving this system. Then the n components of x can be found from solving that system. A transpose A, which we just looked at earlier, A transpose AX is equal to A transpose B. It can be shown that A transpose A is non-singular only if A has full rank, meaning that if A is non-singular, then only then will A transpose A be non-singular. Why is that? Well, if A has full rank, then for any x not equal to 0 implies that Ax cannot be equal to 0, right, because Ax is equal to 0 is going to give me x not equal to 0 only when A is singular, right. So, if A has full rank, if A is non-singular, then x not equal to 0 implies Ax is not equal to 0. Hence, x not equal to 0 implies norm of Ax square, since Ax is not equal to 0, norm of Ax square must be greater than 0, and norm of Ax square, if I think of this as a vector, right, it is nothing but that vector transpose multiplied by itself. So, x transpose Ax, which I can write as x transpose A transpose Ax, must be greater than 0. What does this mean? That means that if A is non-singular, A transpose A is positive definite, because this is the criteria for positive definiteness. What is the criteria for positive definiteness? Any vector x transpose times the product with the matrix times that vector product with that same vector is going to be greater than 0. So, this means that A transpose A is positive definite, hence non-singular. When A has full rank, the least square solution is unique and is given by x is equal to A transpose A inverse. Just by inverting that matrix, we can find x, A transpose A inverse A transpose B. However, when A does not have full rank, there are multiple least square solution of x, right. Then we cannot solve that equation, right. A transpose A is becoming singular, right. When A transpose A does not have full rank, means A transpose A is singular, then we are going to have non-unique least square solutions, right. However, we must keep in mind all of these solutions must satisfy the minimum residual criteria, and since the orthogonal projection of B onto Ra is unique, they are all going to give the same residual vector R, right. What is the residual vector R? Again, it is after we take the projection of B onto the space that is spanned by A, whatever is left is the residual vector R. Since the vector B is known, the orthogonal projection of B onto Ra is also known. The residual vector is also going to be the same, right. So, irrespective of the fact that we have a large we have non-unique x, there are a large number of least square solution x, right, which satisfies the least square criteria, they are all going to give the same residual vector R. When A transpose A is singular or ill conditioned, computation of the least square solution becomes complicated. You can see that because it becomes harder to invert this matrix, right. If A transpose A is ill conditioned or is near singular, becomes hard to invert that matrix, and the computation of the least square solution becomes complicated. An alternative method consists of the decomposition of A into the product of an orthogonal matrix Q and an upper triangular matrix R. This decomposition is known as QR decomposition. It is very important in numerical analysis, and it is governed by the following theorem. Let A be a m by n matrix with m greater than or equal to n. Recall, we are talking about overdetermined systems currently. So, m can be greater than or equal to n, and let us suppose for the time being that A is non-singular, that its columns are linearly independent. So, it has got full rank and it is non-singular. Then there exists a unique m by n orthogonal matrix Q. Orthogonal matrix meanings each column is orthogonal with every other column. Each column, if I take a dot with every other column, it gives me 0, right. So, each column is orthogonal. Orthogonal matrix Q with Q transpose Q is equal to a diagonal matrix, right, and such that each term on the diagonal is greater than 0. What this theorem says, that if A is a non-singular matrix of size m by m, we can always split it up into a product of an orthogonal matrix Q and an upper triangular matrix R, a unique upper triangular matrix R, which has got 1 on all its diagonal terms, and this decomposition is known as the QR decomposition. QR decomposition exists with the stated properties only when A has got full rank. Thus, it is directly applicable if A is non-singular, but A transpose A is ill-conditioned, so that A transpose A is prone to numerical errors. So, if A transpose A here is ill-conditioned, inverting that is a problem, right. So, we can't invert it directly. So, instead of when A transpose A is ill-conditioned, we can do a QR decomposition. You can do a QR decomposition. It turns out that the original QR algorithm, the QR theorem, it assumes that A is non-singular, but it turns out that even if A is singular, it is possible to modify the QR decomposition to solve for the least square solution. We are going to talk about that later on. However, a modified form of the decomposition can also be used to find the least square solution in case A does not possess full rank and consequently A transpose A is singular. So, neither of these two cases, whether A transpose A is ill-conditioned, when solving that system A transpose A inverse operating on A transpose B is going to be hard, is going to be prone to numerical errors, either in that case or in the situation when A transpose A is straight away singular, right. Either in those two cases, I can use my QR decomposition to solve my problem, right. So, we are going to continue with our discussion on QR decomposition next class, and following that we are going to talk about some iterative methods for solving the eigenvalue problem. So, eigenvalue problem in civil engineering, or for that matter any field of engineering, everyone has to encounter at some time the eigenvalue problem, because it is too important. It governs the physical behavior of so many systems. So, it is very important that we know of easy to use efficient algorithms for obtaining the eigenvalues of matrices, particularly for symmetric positive definite matrices, which are commonly encountered while modeling physical systems. Thank you.